Excellent. Well, welcome everyone to AI in Construction. So today I'm super excited to have Icaro Mariani, who's the director of customer engineering, excuse me, at Giatec. I may have got that wrong. I apologize. So essentially, what we're going to talk about today is over the course of the last couple of months, we've talked about AI from a number of angles, and you're hearing about it all over the place. One of the things you hear about in construction so much is how the data isn't that great. So, there's a lot of ways that we can make our data better. One of the best ways to do that is to automate it and use sensors. So, Giatec, one of the things that they do, and I'll let Icaro talk a little bit more about what Giatec does. But what I was really excited about is how sensors are a big part of how they go to market. The second half of that is software that takes that data and does really important things for concrete mixes and so on. And we'll actually have a second session later in the year that talks about the software itself and the more AI applications. So today we're definitely going to be grounding ourselves in AI applications, but a little bit more about construction data and as the kind of foundation, no pun intended, for how to build a better AI application and use it on real projects. So Icaro, you want to just introduce yourself and maybe correct your title? I apologize, but also talk a little bit about what Giatec does so that folks have some context.
Thanks, Hugh. I work as the director of customer and engineering success here at Giatec, and
There we go.
the goal of my team is to ensure that our technology is being used by engineering firms, general contractors, concrete producers to their benefit. So it's a mix between customer success and engineering, and that's why the fancy title, I would say.
Got it. So why don't we switch gears over to your slides? So Icaro is going to walk us through some things that are a little bit more specific to the question. So if you don't mind sharing.
100%. Just give me 1 second to presenter mode. You should see that coming up in a second. Okay. Do you see my presentation?
Yep, that works. We'll pop it into presenter mode. I think it's still, yeah, there we go.
Presenter
all
mode.
right. Looks like we're going to go back in time to where it all began.
Yeah, so I'd like to start here by showing a picture of a concrete batch plant back in the 1900s. And what we see here is like the fancy trucks that we had back then and the concrete being mixed, uh, similarly to the way we're doing things now. So in 100 years, the process of mixing concrete hasn't changed a lot. Of course, we have new technology in batching systems and how to integrate different systems into the cloud. But the way we produce concrete itself, the core of it, hasn't changed. And the way we analyze the data we get out of it is still the same. The slump tests and breaking samples, basically, they're still the same. The only difference we see now is, of course, we have better grading of the aggregates. So instead of using the traditional 6 by 12, we use the 4 by 8 cylinders, but the process of measuring the quality of concrete hasn't changed in like 100 years. And one of the goals we have here at Giatec is actually reshape the way we do things and actually enhance the industry. And that leads me to the second slide, which is what is the goal of introducing IoT and AI in the construction industry? So we can actually integrate everything from batching the concrete at the batch plant, putting it at the job site, monitoring it after the placement, and actually having the go ahead to perform critical operations when the time comes, such as stressing cables in low tension decks or removing forms on high rise buildings. Does that make sense?
Yeah, it does. So what you're saying is you guys are really looking at the life cycle from when it's designed to mixed to put in place to curing to finally you walk away from it.
Exactly. So the goal is to have a fully integrated system where either the GC, the CMTs, the EORs, everyone has visibility of the cycle of that concrete, both from coming directly from the concrete batch plant, also in transit, and then when you're pouring that concrete.
So one of the things this obviously brings up is we talk about AI a lot as if it's a binary, there is this or there isn't that. And a lot of what I find is what sometimes people label as AI is sometimes just pretty good statistics. And it feels like what you're laying the groundwork for, I might use the word foundation yet again, is not just AI, but a range of methods to better understand what's going on. Not everything needs AI. Sometimes just good statistics or good analytics is enough. Did you guys start all this? I don't want to jump the gun too much, but did you start a lot of this saying, "Hey, we've got data, we've got time series, we've got sampling and so on. Let's start with analytics. And wait a minute, we've got more than we thought we did. We can do more with it." Does that make sense?
Makes total sense. So this slide here actually explains a little bit of our first AI model that we implemented here at Giatec. So as you see, we have the app that is controlled by the user and the smartphone that can download an app, can have it, access to it. Basically, our first AI was to identify the pouring time. Because when you cast a cylinder and then you break it, let's say you have a 10-hour long pour. Do you take that in consideration when you're actually measuring your in-place strength? So the first AI model we implemented was in the sensor itself to identify, okay, there was a sudden change in the temperature. Let's say right now it's 50 degrees outside. Conker comes at 70. That sudden change of temperature indicates, okay, that's my pouring time. But let's say it's a spring and the temperature is the same. The Conker temperature and the ambient temperature is the same. We can actually identify, okay, the hydration process is beginning now. So the algorithm behind it identifies based on machine learning that the pouring time correct is this one when the hydration process began. So that was our first model back in, I'd say, 6, 7 years ago. And then it got way more advanced where we stand.
Let me just stop you there. There's something really interesting in what you're talking about. And again, we use AI as a really umbrella term. The first way it was successfully used in the 2010s was to categorize things, was to recognize and classify things. What I'm hearing you say is you guys have built and implemented a model that recognizes when certain things are happening and starting in the concrete, so you can start capturing data. Well, anyway, you can identify what the data means. Is that what you're saying? Is that your model is saying it looks like this is happening? Okay, now we can start from all the data from here on is during this phase or this start at this point in the process. Is that right?
Yes, yes, absolutely. Because if you think about a large pour, let's say we're talking about 1,000 cubic yards, you always needed to have a field technician taking notes. Okay, now concrete is covering that sensor, and now it's covering that sensor, and taking manual notes. With the system implemented, the sensor can actually detect that pouring time alone. So uh, the strength gain begins at that given point of time. It gives more precision to the data you're getting out of the sensors. Because in the end, if you don't know what is the start time, you're actually
Right.
excusing the data in the future.
And I think that's a theme that we're talking about here overall, right? Is that increasingly precise measurements allow you to do increasingly precise other things, whether it's starting, stopping, mixing, so on and so forth. And I think that's a big part of the story, right? Is that because you've got a degree of precision that just wasn't possible before. And we started this whole thing talking about it coming from sensors, but it's really cool to hear that you're actually also have kind of a classification layer that's adding to that accuracy and precision. Very cool.
Imagine that you have different mix designs, and then if you have a patchwork in a viaduct where you're gaining strength in 3 or 4 hours, knowing that start time is actually very beneficial. So that data analytics and the machine learning that came out of the thousands of data points we acquired in the past years actually helped us succeed in that front.
Love it.
Just demonstrating here our footprint across the globe. We are, as you can see, mainly focused in North America, Canada, and the United States, but we have a large footprint in Europe, in Latin America, and also, I would say, Oceania and East Asia. Uh, in this one, I would like to mention the global CO2 emissions to give a perspective of another front we're trying to tackle here at Giatec, which is how can we make the world a better place? And with all the new changes in carbon reinforcing reduction across different states and different countries, I'd like to bring awareness of what if concrete was a country? If concrete alone, including cement, I would say, we would be the third most polluting country in the world, just behind China and the United States. So any cement we can take out of our mixes, any enhancements we can make into our mixes in our processes, we're going to greatly reduce that emissions that are coming from the concrete industry. So not everyone knows about this, but concrete would be the third most polluting country in the world. Uh,
And
and
that
how
that
we're
sets the stage. Well, if I may, that just sets the stage for why a lot of this is important. Is that in addition to just knowing how quickly things are happening and being on top of the progress, understanding what what your concrete is doing is enormous. And I think you're about to get into the other reason this is so important, right?
100%. And that
Yeah.
is just going to be a teaser for our next session. But I would just like to mention what leads to that excessive carbon emission. A lot of it comes from the over design because sometimes you have unreliable testing, you don't have enough data that is not properly organized, raw materials variability. Let's say instead of using VSI crushers, you're using jaw crushers only, or delayed results or weather changes. So a lot in this cycle leads to an over design, both from the concrete producer perspective, but also from a structural engineer design. Because on the other side, you also need your safety factors, right? And everything piles up to have an over designed mix. And our goal is to actually use machine learning processes and AI to, okay, we have a strong data set here from different mixes. And then we can actually pinpoint how much those mixes are being over designed and propose optimization methods based on packing models, based on cement efficiency, and other factors.
So if I can just pull this out one more time, what's really important about what you're saying here with the over design, and you see it throughout construction, is that these are buildings that can't fall down. So if we know that we have imprecise data, you add in padding and you put in more than you need. Analogy I made when we were first talking about this, there's a company called QNect, and they do connection engineering, which is for the steel superstructure. And before them, what wound up happening is there were really only a couple of ways to do the connection design, and they overdid it because they didn't have the ability to. Well, two things. One is they assumed the fabrication of the steel had a pretty wide range, which used to be true and isn't anymore. Not certainly not like it was, but also they didn't have the staff to do the design, joint by joint. Well, now you can automate that, and you do, and they save tons and tons and literally millions of dollars in steel because they can do a better job and they don't have to over design. Seeing that in concrete, which is of course an enormous component for most buildings, is a really big deal. I think there's a bigger point than just concrete. It's the point that better data means that we can use less materials, have less impact on the marketplace, or sorry, less impact on the economy and the environment, but also not give up any safety or utility. So what you're saying is you guys are really pioneering the ability to actually know how much concrete you need because A, you're using better mixes, and B, you're understanding how much of it you need way more accurately than was true before. Is that a good summary?
Yeah, that is an excellent summary. Yeah, we're using that in that front, and specifically when you have a better precision, when you have a Gauss distribution or a normal distribution where that you can validate that your process and your machine learning is kind of yielding a nice result that is compliant with your safety factors, you're going to be on track to reduce your not only reduce your carbon footprint, but most importantly, I would say reduce your costs, right? Uh, Take consideration, let's say if I'm not mistaken, the Vancouver market alone in BC, Canada, the concrete market there is about 4 million yards a year. Imagine that you reduce, of course, that is distributed in different concrete producers, but if you shave off $1 or $2 a yard, we're talking about $4 million just in savings. So that is what we're aiming for, not only the carbon reduction, but also bringing that financial advantage to concrete producers. And here, just an example, like a 30% CO2 reduction in this example. But that was basically a teaser for what is coming up. We're going to dive into more in the future session, but talking about the actual strength in the job site, how we can actually do that. The process is basically this. You have the concrete batch plant, and then you move it to the job site, you transport it, then you put it. And what you need to do is cast the samples to validate that the concrete that was received is indeed what it was requested, right? And then you break those field specimens in the lab. Later on, because those samples they stay at the job site for 24 to 48 hours in a cure box, they're transported to the lab, and then the lab breaks those samples, call the project, and lets them know, okay, you're good to go. Remove your forms, stress your cables, move on. But this process can be delayed. And the whole goal of using sensors is actually prevent this from happening. So you can have a direct correlation on the job site, triggering alerts to all users, letting them know, hey, you're safe to go. You can remove your forms. You can optimize your team's efficiency. That makes sense.
Very much.
And just an example here that the variability you get out of samples, I'm not saying this is throughout, okay? But this images like this can happen. Otherwise, those pictures wouldn't exist, right? So we have samples being stored in the high heat of Texas on the left-hand side during summer, or just being dumped on a truck to be transported. And having this type of uh, care with the samples can lead to huge mistakes, such as a blowout in a PT deck. So when you have a blowout, that picture is very impactful, in my opinion, because it can actually harm and even kill people. If you don't have enough strength, and then you're stressing your cables, anyone close to this can get harmed. So another facet to what we're trying to do here is actually bring more safety to the job site processes as well. So you can avoid things like this from happening. Does that make sense?
Yep, very much.
Cool, cool. So what I would just like to bring that parallel to what we're doing on the AI side, what we do in terms of concrete strength estimation with our IoT sensors is actually backed by different codes. Okay, so ACI 318, 228, 301, even 207 for mass concrete, they refer to the maturity method. ASTM as well, so the American standard, I would say, is the backbone standard for maturity across the globe. A lot of different codes reference and points to ASTM, including the Canadian one. CSA points to ASTM in terms of the maturity method. And also different, Euro codes, the Dutch code, 5970. So we have this process of maturity being widely accepted throughout the globe. And that is allowing us to use more data to kind of grow our AI side of things. If that makes sense.
Yep.
Here is just an example of maturity acceptance by DOTs. So if you see a lot of the states, they are accepting the maturity method. Some of them, they are in progress of accepting it. And some of them, they are not quite there yet. So what we're seeing is that the majority of DOTs across America, they are accepting the maturity method as means of calculating your strength. I don't want to dive into the details here, Hugh, but basically the process of estimating this is having an area under the curve. So the assumption of calculating strength is if your area under your temperature profile is the same for any given mix, it means that you have the same strength. The biggest advantage here is that on your left-hand side, your structure on site is generating a peak temperature because it has a mass effect compared to a cylinder that have this process spaced out. What happens is that you gain strength much more rapidly at the job site compared to a sample that is being cured at a lab condition. That's why you can move faster installing sensors on site.
Let's unpack that a little bit. If you can go back. So I just want to make sure we're unpacking this. So what you're saying is the difference between the time it takes in a laboratory environment versus on site it can often be significant. That it's slower in a lab because of the form factor they're using, versus a site where there's a lot more surface area. Presumably, is the point where it absorbs the temperature more easily. Is that right? Is that the form factor of a real kind of on site? It gives it a lot more. So I would assume it's surface area, or is that not what's going on?
I would say it doesn't dissipate as faster as a cylinder because on the one hand we have a 4x8 cylinder, which is a very small volume, right? Imagine if you have a mat foundation that is, I don't know, 5 feet thick. and 30 feet wide, what you have is a mass effect that retains that heat for much longer, and therefore your hydration process is stronger at the early ages, and
That's
therefore you
interesting.
gain more strength.
So it's not surface area; it's the opposite. It's that there's more mass there. I got it. You actually said that. I just didn't catch it. Awesome. Thank you.
Exactly.
And your point though is that you can't trust that if you're not measuring it. So by putting sensors in there, you can say, okay, we know what's happening. We can trust it. We're not just relying on models. We're actually looking at what's actually happening on our slab.
Absolutely. And the opposite can also happen. Let's say you are in New York City and then it's 20 degrees outside, okay? You are during winter. What happens is if you take those samples and put them in a very nice warm bath of 72 degrees, and your structure is actually at, 35, 32, you just see that dissipation very rapid. What can happen is your samples are overestimating what your structure is actually doing. So you're actually using the sensors for safety purposes, not only for gain time and money. Does that make sense?
Yep.
Yeah. So that's one of the goals, and having an integrated system allows you to have the sensors, have a modem. That modem connects to the sensors. We call it Smart Hub, and triggers push notifications 24/7 to users, letting them know, okay, your temperature is too low. Go back to the job site and turn on your heaters, put blankets, or take proactive measure before you run into a non-conformity.
Yeah, I've heard people say the warmest place in Calgary in the winter is where they're pouring concrete.
Yeah, yeah. In Calgary during winter, we can go to -40. So
Yeah.
that is tough. And I say -40 because -40 is the same for Celsius and Fahrenheit.
Oh,
So
that's
it's
funny.
bad for
There
both
you go.
sides.
So the lines converge.
Yeah. But here is an example of what we're doing here. So the sensors can actually capture your temperature, right? And convert that to a strength based on the maturity method. So even though you're using the same mix as we have here, we have three different curves. This is Chicago, by the way. That was, I believe, October last year, if I'm not mistaken. So what happens is your black line, which is your element, is peaking 100 degrees and then slowly coming down to reach thermal stability. Your red line is your field specimen that was poured from the same truck, left on site overnight, and left on site throughout. And then the blue line is your lab one, which was left on site for the only first day and then moved to the lab. So you see that despite being the same mix with the exact same proportions, the behavior is not going to be the same. And what we see out of this is a difference in the strength gain. So if we compare our element versus our field, we're having 2.5 days to achieve 3,500 psi. 2.5 days. So that is huge. So sometimes you're just waiting for that result to come in while your structure is already there. It's already on point. You can move on. So the time savings you can get out of sensing devices can actually be measured through this type of analysis.
And just to reinforce a point you made earlier, in something like 47 U.S. states, this is something that a inspector would work for an inspection. This matches what certainly you were saying DOT will accept, but this as opposed to what may or may not be in the spec it is acceptable for a lot of AHJs, correct?
100%, because
Yeah.
ASTM C1074 is the standard. So if you're outside a DOT project, let's say it's just a high rise, and you are in the United States, yes, it is accepted. That is
That's great.
just the DOT acceptance because they follow AASHTO standards, right?
Ah,
So that's why it's a little bit different, but the concept is the same. So 47 states, they accept the maturity method for DOT projects.
got it.
And MTO as well here in Canada. Just our difference is that it's not provincial, it's like a federal, but we follow ASTM as well. In terms of applications, where can we use this? Literally in a lot of places. Mass concrete, opening traffic, post tensioning, formwork removal, even saw cutting. When you want to cut to provide your, your construction joints, you need to pinpoint, okay, I have 500 PSI there. You can actually use sensors to pinpoint that for you. Precast, even shotcrete. To be honest, like we used the sensors at the Roundout project in New York. Over 1,000 sensors were used for shotcrete only. So I know it depends on the nozzle person, but as long as the sensors are properly installed, you can actually measure the strength of your element in shotcrete as well.
And back to the AI application of this is this point that across all of these different applications, form factors, and environments, your model is able to recognize and kick off the maturity calculation, right? I mean, that's the magic here. It isn't just that there's a sensor; it's that the data is being fed into a model that can identify when things have started and then when they've likely ended.
Yes, and more than that, Hugh. You know what? When you create what we call a maturity calibration, because for the sensors to work, you need to calibrate the mix design. What happens is you create the maturity calibration by casting samples, breaking them, and actually measuring the strength. So when we create this, we can actually feed the system with the mix proportions. So let's say you have 500 pounds of cement type 1, 200 pounds of fly ash type C, whatever. You can actually pinpoint all your mix proportions. And once you do that, the system is actually validate if your maturity makes sense. It's going to pinpoint, okay, your numbers, they do not seem correct for your mix proportions. Because your mix proportions are telling the sensor that you should be performing much higher or much lower than this. So it actually validates if you have done your calibration correctly. So that is another layer of confidence you can apply by using the sensors.
But interestingly, as we look more and more at concrete options that reduce carbon, embodied carbon, I have to imagine that's an important part of the mix, right? Because these low carbon concrete types that are coming onto the market are almost definitely going to have different mechanical properties than what they're replacing. They're no matter what, they have mechanical properties that you have to consider. So I got to imagine what you just described allows people to introduce new concrete types more confidently because you're not just dumping it into the mix, you're checking how it's performing and so on. Is that one of the ways that you're hearing this sort of capability get used by people?
Yes, because you can actually identify that. And more than
Yeah.
this, we can also measure both the compressive and the flexural strength. That is approved by code. So if you have a DOT project, let's say a pavement where your target is not 5,000 PSI, it's actually 400 PSI because it's flexural, the sensors can actually measure both. You just need a calibration and then you just tweak between flexural and compressive, and the system just back calculates everything on your behalf.
Got it. That's great.
And the system, like, I don't know if you can see my screen, my camera, but
Yeah.
the sensor looks like this as I have on the palm of my hand. And it's super simple. It's very intuitive. You have a QR code where you're going to tag, use the app, you turn it on by removing the probe from inside. It flashes 3 times and you're ready to rock. You just need to install this onto your river, no more than 2 inches, pour the concrete on top, and start measuring your strength and temperature. It's as easy as that.
Very cool.
And the data analytics that you're going to get out of it is, your strength, your temperature, your target. Okay, I'm 50%, 51% I'm missing 49 to reach my target, basically. It shows you a progress bar. But more than that, it actually triggers push notification to you and other team members that you select to let them know, okay, I reached my target, let's move on. Does that make sense?
It does. How deep into the concrete can it go? Because what I'm getting is you buy all the concretes and they're effectively consumable. Like you don't ever get them back. How deep in the concrete can it go to have the radio signal still come out?
So it depends on what you need. So the beauty of the sensors is that they are dual. So you're taking a measurement at the tip of this probe and actually inside this logger. So this logger must be no more than 2 inches from the surface. So because you need the signal. But then this cable, you can extend up to 100 feet, depending on how long your element is.
Got it.
It comes in
That makes
different length. Yeah,
Yeah, right. Well, you solve the radio problem by having the transmitter close to the surface, but the sensor can be anywhere you want it to be.
100%, yes.
Yeah, that makes sense.
The good thing is that operates via Bluetooth and also LoRa. So if you are using LoRa technology, your smart hub can connect to the sensors up to 1,000 feet. So if you have a high-rise building, 40 floors or 50 floors high, you can just put a modem on your trailer and it's going to capture your entire job site, one modem. That is the beauty of it.
Very cool.
Uh, and like as we mentioned, it can be used in like different projects, like in tunnels, in bridges, patchwork. Wind farms is a big one. So renewable energy across the United States recently, I would say the past 3 years, I cannot precise a percentage, but a lot of sensors were used in different wind farms. A lot
And
in Texas, by the way.
why wind farms versus something else? What is it about wind farms? Is it just that they're conscious of their environmental impact, or
Both. So they're being conscious about the environmental impact, so they can actually check how the mix is performing, so they can actually present the producers with opportunities to enhance the mix. But more than that, following ACI 207, they need to respect temperature differentials. Because the sensor measures body and cable, you can actually calculate the difference of temperature between one and the other. And what happens is, and that is in my next slide coming up, Hugh.
yep,
If your temperature difference is too high, you're going to have cracks on your concrete. So you need to respect a 35, 40, 45, depending on the spec, limit to prevent thermal cracking. And that's why the sensors are being used, because the pedestals, they are huge. So they need to put a sensor in every single pedestal to track these differences.
so that's it. Is it this mass effect you were talking about before has a downside when there's too much mass all in one place? Is that what you're kind of saying? Is the pedestals are just a big lump of concrete, so they can have problems with the interior cooling at a different rate, or in the case of Texas, warming at a different rate from the exterior, especially during the day. We were talking about how the difference between morning and evening I'm in Austin, which is not out in East West Texas where a lot of this is. It's a 30 to 40 degree difference within one day. So this issue of differences in cooling rates has got to be a big deal.
It is a big deal because imagine, so the Hoover Dam, for example, it took years to cool down. Years, I'm talking about decades to cool down because the volume is so big that the heat inside it is trapped and it doesn't dissipate. So what happens when you have a pedestal or even a mat foundation? Anything that is the minimal dimension is 3 feet. That is the rule of thumb for mass concrete. If your lowest dimension is 3 feet, it means that is massive. So what happens is your heat is trapped, but your surface is trying to cool down. And that generates a temperature differential. In Texas, for example, you're saying that at night, your temperatures can go to 60 or 50, right? But if your core is at 120, 130, what happens is that even though it is not that cold outside, it is generating a temperature difference that can make your concrete crack.
Yeah.
That's why even in hot places, it's important to protect your element and be conscious about that temperature difference.
Really interesting.
Another thing that we have in our plate here, and I'm pretty proud of that because I believe this is a breakthrough in technology, is the SmartRock Pro. So this is the SmartRock Pro in my hand. It is composed, you have two main components here, but basically it doesn't need a calibration. So it's a self-calibrating sensor. It's mix independent. So if your driver is adding water to a mix design on site, or if anything is happening to that specific load that a temperature sensor wouldn't capture, this sensor can because it's mix independent. It self-calibrates when it actually detects when it only activates when it's fully covered in concrete. So it's a step ahead in the game of concrete strength measurements. Yeah, so I would say this is a game changer. Is We are in the early adopter phase right now. So only selected customers that applied some time ago to purchase the sensors, they are receiving them. But soon we're gonna have it roll out across North America. So yeah, it's gonna be a game changer because eventually our goal is you don't need cylinders anymore or samples anymore.
Wow. Okay. How,
Does that make
how
sense?
we'll talk a little bit more about why you won't need sensors or cylinders anymore. Why this self calibration versus the other sensors makes that difference.
I can talk about it a little bit more then, Hugh. So
Okay, please.
basically, this sensor, it follows the STM C1074. It only replaces your field specimens. It doesn't replace your lab specimens, right? So only
Got it.
the ones for the early ages. This sensor, it is a patent pending technology, okay? It is not approved by any standard so far, so it can't replace anything, right? But in the long run, if the sensor proves to be measuring correctly your strength on site, it can actually be a true representation of your structure because it's going to take in consideration any tampering that might have happened with your mix design. As a rule of thumb, people only cast samples every 10 trucks, every 100 yards. That is typically what we see, right?
Hmm.
So what if you're missing those 9 loads in between, right? That you are actually, that sensor is
Hmm.
actually installed in your element and capturing what is going on in your element with regards to temperature, with regards to humidity, the air that your mix has. So you can actually measure it correctly what is going on in your structure.
Very interesting. Wow.
Uh,
Okay. Hmm.
and this is what we were discussing in the past, just explaining why the thermal crack occur. Basically, if your core is too hot, it's trying to expand, right? And then
Yep.
your surface is cooling down, it's trying to contract. And those tensions that are created by this trying to expand and that's contraction due to restraint, it can actually generate a thermal crack. And that's how maturity can help. If you know that you have enough strength in your element, it means that you can boost your differential from 35 Fahrenheit or 20 degrees Celsius to 25 to 30, so on and so forth. As the sensors can measure your strength, they can actually tell you, okay, even though the temperature difference is very big, you are still safe because your concrete is strong enough to withstand the tensions that is being subjected to.
And is that why the sensor, the second sensor, has the two knobs so it can sense what's going on like physically?
Uh, this sensor also, yeah, the Smartrock 3s, they have the two, so you can actually measure two locations at once. The new one only measures one location so far.
Right.
So we are in the initial stages. This is, let me show you. This one is the transmitter, so the antenna that is going to go at the top. And the other one is where you're taking the measurement. So
Oh, I
this
see.
one
Got it.
only measures one location. So
But is it measuring actual strength? Because you've got the two kind of knobs that are, is that why it's shaped that way? So you can actually sense, strength and or tension?
yes, you nailed
That's
it.
really,
Yeah.
yeah, it's really interesting.
So
Yeah.
it's a new technology. It's patent pending, as I told you, but I joined Giatec 6 years ago. That product was in the works already. So it took a lot of work to bring this to the market, and this is going to be a game changer.
Really interesting. Well, it speaks just kind of going back up to the application of data generally, but AI specifically. When you've got that kind of accuracy on the ground, it has a huge impact, of course, on the models you can use, right? I mean, one of our problems always with AI is that garbage in, garbage out, and if you're able to put high quality, accurate data that is, in this case, of course, automatically labeled, you're not only able to do good inference, you're able to build better models over time. which is pretty exciting.
100%.
Hmm.
And just to close the loop here, talking about machine learning specifically, uh, we have a feature in our cloud because all the information from the sensors, they go to a cloud dashboard where we can see the data, mass print reports, actually where you can manage your data, right? We have this system that allows you to, okay, I have a project in Austin starting on Monday. So you can actually pinpoint the location. You can mimic your element dimensions. You're going to put what is the protective equipment that you're going to use. Let's say if you have wood forms on the side, blankets on top, you can actually build that model. Enter your mix proportions, as you see here at the bottom, the type of cement, how much water, fine aggregate, slag. And what the model is going to tell you is how your concrete is going to perform in the future based on your location. So depending if the temperature is dropping a lot, you can actually take proactive measures such as purchasing blankets. Or if it's in the high of summer, you can ask your producer to start adding ice to the mix. So you don't reach a super peak, a super high peak, for example. So it allows you to mimic your element even before you pour your concrete.
Question for, especially when it comes to the Smart Rock Pro, how long do you continue to get data from it? Will it last for, a year or two? Because one of the other interesting things that this opens up the possibility of is you hear people talk about there's just not a lot of data about what's actually happening in buildings after things are installed, whether it's the trades or the GCs, they move on to the next job. And a lot of the standards we have are based as much on experience as they are hard data. Because again, the people usually that are responsible aren't necessarily building operators. They're usually, product and material installers, like the contractors who don't check 5 years later, right? So the fact that you knew that the Hoover Dam took a decade or so to cool is probably because some scientists wanted to go check that out. There probably was a question because it's such a crazy mass of concrete, but no one would normally know that about a normal building. You know what I mean? Like no one would pay attention. So the fact that there's some amount of data in the operating building afterwards is already kind of really different. But how long, and I'm assuming you don't build these to last, to continue transmitting data for, 10 years. But what is the expectation for how long they'd still have data?
So the sensors are mainly designed for early age operations. So they're going to transmit data for up to 4 months, but the
Okay.
memory ends at 2 months and it doesn't override. So we have 2 months worth of data out of the sensors, both the
Got it.
Pros and the Smart Rock 3s.
Got it. For now.
Yeah, for now. So if we see
Until
there's a,
until some owner says, I'd like to know more, but that's okay. You're still getting a patent. That's like early days. That's really exciting though. The idea that you're putting sensors in where, and a little bit more engineering, you could say, well, now we want to know how this performs for the next 2 years. That's just product decisions. It's not like it's technically difficult. It's just someone has to pay for it. That's really interesting.
yeah. And I would say one of the reasons why dams are actually measured more carefully, it's because of the safety factors included on them,
Right.
right?
Yeah, yeah,
Yeah.
yeah. Yeah.
Uh, not, yeah. All the structural engineering design, all the safety factors are based on probability of death. So you cannot go into a building and increase your probability of death compared to walking on the street. So that's why we have like that is the deep foundation of every safe margin. And that's why dams they have the safety margin much bigger, right?
Yeah.
Uh, and I believe that was this is my last slide. It's just a teaser for what is coming up. What is Giatec's vision ultimately is integrate everything into one single platform. So data from the concrete batch plant, AI models analyzing all the data. So Roxy and the big data analyzing data coming from batch plants, coming from the job site. And that is being fed to SmartMix, which is our platform, and also tracking the data from concrete in transit. So that concrete that is being transported to the job site would also be included here.
Very cool. Well, this perfect timing. That's about how long I was hoping we'd go. We've got some folks on the call. Are there any questions from folks that are listening? We've got a couple minutes left. More than happy to entertain. While you guys think about that, either unmute yourself or pop it into the chat if you like. But I think this is really interesting for me because again, it speaks to where we see construction going in a way you don't hear as much, which is increasing precision in how things get done. Reduces the variance and reduces the padding, for lack of a better word, people need to put into things. So you just get a lot more efficiency out of it in every sense of the word. It takes fewer people, less time, less material. Really, really exciting to really start to get just more accurate. And essentially you're optimizing, right? You're doing what people do in manufacturing, you're doing for concrete, where you're using data and process to optimize the concrete pour. Really cool.